All right, once again, as with the previous example, the reason I have this up is because we need to identify the difference between m of x and x. M of x is the Richter scale magnitude, and x is the seismograph magnitude. All right, so I've changed up this problem a little bit, which is why it's a little shoddy here in the words there. But the process is still the same no matter how you look at it. For example, the problem on the homework, we talked about the San Francisco earthquake and some South American earthquake. Don't worry about the historicity of those. We're not so concerned about historical accuracy as we are with just the ability to solve a problem like this. But keep in mind that we are going to be using the same formula as we were before, which is right here. And again, m of x, that would be a Richter scale reading, and x would be a seismograph reading. Now notice for these two, we have two Richter scale readings, and we need to compare the two. So we need to figure out what their seismograph readings are between these, all right? Otherwise, we're going to have these just a little bit wrong. And naturally, if we were to compare them side by side, 9.1 and 5.3, that would be too easy for this class, and so naturally we've got to use this logarithm stuff because, again, we're talking about growth and decay, particularly in terms of exponents and logarithms. So let's look first at the 9.1 reading, and we'll figure out what that was on the seismograph. And again, I'm just going to use this equation to set this up. So this is what I have. I have the common log of x over 0.001, or 1/1000th. And this equals 9.1. But it may be important for us to remember that the base for a common log like this is 10. Because what I'm going to do is change this into an exponential form so that it may be a little bit easier for us to solve. So the base is 10, so I still have that 10 with now an exponent of 9.1. Which makes this thing look a lot easier, and this equals what it was the natural log of, and that is x divided by 0.001. From here, we just need to solve for x by multiplying both sides by 0.001, and that is because this is divided by 0.001. If I multiply it by itself, by what it's being divided by, then I would have a coefficient of x that is 1. Alright, so this is what I have, and again, these two cancel out right here. So we still have the x, and we simply need to solve this, which we can do on a calculator right now. And I get this large number, 1,258,925.41. And I need to compare this against the 5.3 reading. So the setup is the same here in our original formula or function. And once again, since I'm going to be changing this into exponential form, it may be helpful to identify the base, which is 10. So I have base 10 to the power of 5.3 equals x over 0.001. And from here I'll just multiply again both sides by 0.001. And that will cancel out these 1/1000ths, and I'm left with the x, and all of this stuff here I can just put right into the calculator. And this is about what I get right here with the decimal. So that's the reading on the seismograph from a 5.3 Richter scale reading. Now I can compare these two to figure out how much bigger this 9.1 reading was compared to this 5.3 reading simply by dividing these two. And when I solve this, there's a decimal there. When I solve this, that will tell me how many times bigger this 9.1 reading was than the 5.3 reading. And this is about what I get, which I can label right here. So that is how many times bigger that reading was than the other one, which is quite substantial in terms of the grade of an earthquake. Of course, this is a made-up situation, so Perhaps real earthquakes aren't so drastically different in terms of how big they are, but some places have very small earthquakes compared to, like the San Francisco earthquake of 1906, which was very, very big.